Welcome back to the deep dive. Okay, let's get right into it. Today we are zooming in on a piece of technology that's, well, it's so small it's practically invisible, yet it's fundamentally reshaping the infrastructure for AI and for future high-speed data centers. We're talking about dual-mode CMOS MEMS vertical comb scanning micromirrors.
It sounds like a mouthful, I know.
Yeah.
Incredibly technical. But the concept underneath is actually quite elegant. We're looking at microscopic moving mirrors actuators that steer beams of light.
And this research is critical, right? Because it represents a sort of transition point.
It really does. We're
Yeah.
moving beyond the old limits of Moore's law and into what a lot of people are calling the more than more era, or MTM.
The era where you stop just shrinking transistors and you start, diversifying what the chip can actually do.
Precisely. It's a move away from the classic system on chip, or SOZE, which is all about pure computation. We're heading toward a heterogeneous on-chip approach, HOC.
Which means integrating things that aren't just for computing.
Yes. Sensors, actuators, actual mechanical moving parts, like these mirrors, right alongside the standard silicon.
So the mission for this deep dive is to really understand how these highly engineered micromirrors manage to be low cost, high speed, and compact all at once, because that's what's crucial for everything from, say, next-gen LiDAR in cars to high-res VR and AR headsets.
Exactly. At the end of the day, they're converting electricity into mechanical movement to skewer a laser. And the speed they scan at determines your resolution, your frame rate. If you want a sharp, high data rate image, you need a mirror that can move thousands of times a second with incredible precision.
Okay, let's get straight to the specific component here. The vertical comb actuated scanning micromirror, VCAS for short. I'm curious why this specific design, what makes it so much better than the older MEMS methods we've seen?
Well, if you look at the history of MEMS mirrors, they all had pretty major flaws. For instance, electrothermal mirrors. They use heat to move, which made them slow and just massive energy hogs.
Right, and then there were the electromagnetic ones.
The electromagnetic mirrors, yeah. They needed an external magnet, which completely destroys the whole compact idea, and they operated at low frequencies. And don't even get me started on piezoelectric actuation. It was technically complex and suffered from, well, really poor uniformity during manufacturing.
So VCS gets around these problems by stacking the electrodes vertically.
That's the key.
Yeah.
That's the main structural difference. Because the electrodes are arranged in these vertical cone fingers, the VCAS micromirrors offer a huge force density and really high resonance frequencies.
Okay, so more power in a smaller space.
And crucially, that structure means the force is mostly parallel to the direction of motion. That nearly eliminates the catastrophic pull-in risk.
Ah, pull-in, that's the short circuit, right? Where the electrodes just snap together and stick.
Exactly. It happens when the electrical attraction overcomes the mechanical spring force. VCS design makes that incredibly unlikely.
That makes perfect sense. It's like designing a hinge that's, almost impossible to bend too far back. And that predictability must allow the engineers to really optimize for performance. What are the key metrics they're trying to max out?
They're juggling three main factors. First is the field of view. That's just how wide the mirror can scan. Think of it as the maximum angle your LiDAR can cover.
The bigger, the better.
The bigger, the better. Second is scanning efficiency. This is critical for things like battery life and heat. It's how much scan angle you get for every volt you put in. You want a really big swing for just a tiny electrical push.
And the third factor must be about speed.
It is. It's pixel throughput. This one measures the total data rate or resolution the system can handle. It combines the scan angle, the mirror's diameter, and its resonance frequency. Basically, if you can scan wide and scan fast, you can project a high-resolution image like QVGA without any blur.
This is where it gets really fascinating for me. To maximize all three, you can't just guess. You have to accurately predict the performance of this tiny, complex, vibrating part. So how do they even begin to model the motion of something this small?
They start with a really rigorous framework. They use a theoretical 2D model based on Euler-Lagrangian equations.
Yeah.
Now, don't worry about the math, but conceptually, this is the gold standard for defining how a complex, coupled mechanical system moves. It captures everything. The inertia, the spring constant damping, and the really challenging part, the highly nonlinear capacitive torque.
I remember reading that the capacitive torque, the T, was so complex they needed a special approach for it, a hybrid capacitive force model. Why is calculating that specific torque so difficult that, standard 3D simulation tools just fall short?
It all comes down to the geometry of those tiny comb fingers. When you apply a voltage, The electrostatic force that generates the torque is highly dependent on the electrical fringing fields. The non-uniform electric fields right near the edges and the gaps of those staggered electrodes. A standard 3D finite element method, or FEM, is computationally just, massive, and it's often inaccurate when trying to map those rapidly changing fields across the whole structure.
So instead of trying to model the entire thing in 3D, which is slow and messy,
They used a hybrid approach. They combined a simplified 2D FEM analysis focused just on the torque-generating region of the combs with an integral calculation. It gives you the efficiency of a lower dimensional model, but keeps the accuracy you need to define that crucial nonlinear torque. It just makes the whole thing practical.
that's a huge analytical shortcut, but modeling is only half the battle. You need to know these things won't shake apart. Let's talk about the reliability analysis. What are the essential torture tests they ran?
There are 3 critical checks. First, you have to check the torsional fracture strength.
Yeah.
You have to estimate the absolute maximum scan angle before the silicon springs literally snap.
And silicon is pretty brittle.
It's brittle but strong. It has a max strength of about 2.4 gigapascals. Their analysis estimated a mechanical max angle of 54 degrees, which gives them a massive margin of safety.
54 degrees for a microscopic spring is, frankly, astonishing. What was the second check?
Pull-in analysis.
Yeah.
Like we said, VCS is inherently pull-in resistant, but manufacturing is never perfect. So they have to run simulations to see what happens if, say, the comb electrodes are misaligned by just 100 nanometers. Even that tiny flaw can introduce instability. Their analysis confirmed the design is robust enough to prevent pull-in, even in those worst-case scenarios.
And finally, the one that really matters for cars and industrial use, shock resistance.
Correct. Shock resistance. They verify the device meets the really stringent JESD 221 standard. That's the automotive industry requirement. The device has to withstand a mechanical shock of over 3,000 Gs of acceleration.
3,000.
And their device was verified under a shock response spectrum, proving its ruggedness up to a massive 6,176 Gs.
Wow, that's that's surviving a serious impact. It's hard to even contextualize that, but it's far beyond what most commercial electronics could ever handle.
It proves it has the mechanical robustness you need for deployment in a car or, an industrial robot.
Okay, now we have to get to the challenge of resonant systems, which is taming the chaos. Resonant systems are great for efficiency, but they can be really prone to nonlinear dynamics. If you push them too hard or at the wrong frequency, they can jump wildly or just lock up. You have to map that out.
Absolutely. The multi-axis nature of these dynamics can lead to chaotic behavior, things like parametric resonance and bifurcation. If you're a user trying to operate this device, you need to know exactly which voltage and frequency combinations are going to cause the system to become unstable. You have to find that stability boundary on a voltage-frequency plane.
And I assume mapping that boundary by physically testing every single combination would just take forever. So how do they do it efficiently?
They use an advanced analytical tool called MDOF, or multi-degree of freedom, numerical fluctuate theory.
Fluctuate theory.
Right. Think of it like this. If you're pushing a kid on a swing, there are certain timings and forces that will make the swing go really high. And there are other forces that will cause the swing to wobble uncontrollably or jump off its axis.
So Fluctuate theory tells them exactly which forces and timings to avoid.
It's the efficient predictive tool. It allowed them to successfully simulate and then experimentally verify what engineers call Arnold tongues.
Arnold tongues.
Yeah. Imagine a diagram where the horizontal axis is frequency and the vertical axis is voltage. The Arnold tongues are these tongue-shaped regions on the map that represent the unstable zones, the danger areas where the device will jump or lock up due to what's called in-phase parametric resonance.
So instead of wasting time testing, they have a predictive map. It says, okay, avoid this whole area and your mirror will operate stably. That's a huge leap in predictive control.
It is. And using that stability map, they could focus their optimization efforts. They use parametric studies to refine things like the electrode gap and the spring width to maximize performance within the stable zones.
And what were the final results for this highly optimized resonant VCAS mirror?
The performance was very high. They achieved a resonance of 19 kilohertz, which is excellent speed in the out-of-phase mode. That makes it immediately useful for QVGA projection systems. But most importantly, the optimization pushed the optical scan angle from an initial 24 degrees to a huge 36 degrees.
That's a massive jump in the field of view, and I recall they used vacuum packaging to squeeze even more performance out of it, right?
They did. When they packaged the device using LTCC technology and sealed it in a vacuum, The quality factor, the Q factor, skyrocketed. The Q factor measures how much energy is lost during each oscillation. In the air, it was about 48. In a vacuum, it jumped to 100.
For the listener, why does doubling the Q factor matter so much?
Well, a higher Q factor means less damping from air resistance. It's like switching from a swing that's really sticky to one that's almost frictionless. You need significantly less electrical energyless voltage to maintain that same massive 36-degree oscillation. This led to an overall efficiency increase of 164% on one metric and 228% on another, all while consuming just 2.89 milliwatts of power.
Incredible. That's the peak performance for the custom device. But now we have to shift focus to the other big part of this research, the breakthrough that really impacts manufacturing. We're talking about making a VCS mirror using only the materials you'd find in a standard commercial semiconductor foundry. What does this mean for scalability?
This is the novel integration part. The pure CMOS stack non-resonant VCSS. The manufacturing leap here is enormous. They leverage a mature existing 0.18 micron CMOS foundry process. This is the definition of being ready for mass production.
So they didn't have to invent new materials or add expensive, exotic steps to the process to get the mechanical movement.
Exactly. The staggered vertical combs that are needed for the VCAS actuation. They were formed intrinsically just by layering the existing metal layers in that standard CMOS stack. All it needed after fabrication was a simple, improved, two-step front-side etching process to sort of release the structure from the bulk silicon. This hugely reduces complexity and cost.
Using only existing layers sounds great for cost, but standard CMOS layers, especially with 6 metal layers stacked up, are notorious for having residual stress built in. Doesn't that stress cause the mirror to warp and ruin the performance?
It absolutely causes physical deformation. They measured a vertical offset of 5 microns and a curl of about 6.6 microns, and this required them to develop a specific stress-adjusted model to account for those deformations.
And this is where the engineering insight gets really cool. Most engineers would see that residual stress as a flaw, something to get rid of.
That's right. But the critical finding here was that their modified model, the one that incorporated the measured stress, aligned almost perfectly with the experiments. The prediction error was less than 3%. And even more importantly, they found that the residual stress actually enhanced the capacitive torque.
Wait, it made it better. That sounds like turning a bug into a feature. How would the stress enhance the torque?
Think of it like pre-tensioning a spring. The slight measured curl pre-deforms the mirror, which slightly changes the minimum gap between the fixed and the moving comb fingers. When they apply the voltage, this modified geometry creates a better leverage point for the electrostatic force. You get a more powerful mechanical response for the same electrical input.
That is just brilliant design optimization. You're using the forces inherent in the low-cost manufacturing process to boost the device's efficiency. So how did this non-resonant, pure CMOS mirror perform in the end?
By optimizing the electrode gap and, maximizing the benefit of that inherent stress, the design achieved an optical scan angle of 22.5 degrees at 70 volts. This was a critical achievement. It was noted as the best of reported works for this specific category of mirror, and it represents an 81% improvement over earlier designs. It really proves that high performance can be achieved without the expense of specialized materials.
This has been a truly impressive deep dive into the microscopic hardware driving tomorrow's optical networks. Let's try to summarize the 2 main takeaways for you.
First, we saw the incredible lengths the researchers went to optimize the resonant VCOSH performance. They gave it full operational control by mapping out those stability regions using flow-K theory, and they achieve a high-speed 19 kilohertz resonance and a 36-degree scan angle. That's essential for high-performance applications like LiDAR.
And second, we witnessed the manufacturability breakthrough, the successful creation of a high-performance VCS mirror using only the layers available in a standard commercial CMOS stack. That standardization and miniaturization, it's absolutely key for large-scale, low-cost adoption.
And if we connect this back to the bigger picture, this work is truly foundational. This kind of technology is the bridge for integrating advanced CMOS MEMS into silicon photonics. This is what enables the next generation of large-scale optical circuit switch networks, OCS networks, and those are crucial for low-power, high-speed data communication in future AI data centers.
Which raises an important question for you to mull over. Given the reliance on that stress-adjusted model for the pure CMOS mirror and how that inherent residual stress was found to actually enhance the torque, How will long-term reliability factors, like, say, air leakage into the package or material fatigue, influence that initial efficiency gain? Will the benefit of that pre-tensioning degrade or shift the mirror's performance over, say, 10 years of continuous operation?
Something to explore on your own as these devices move from the lab into massive, real-world commercial deployments.
That's it for this deep dive. We hope you feel thoroughly informed about the tiny mirrors making huge impacts. See you next time.